Now we want to talk about what derivatives tell us about a function. First of all, I want to review the fact that we talked about critical points already. That's where the first derivative of the function is equal to 0 or it doesn't exist. The other thing I want to talk about is what it means for a function to be increasing and decreasing. A function is increasing on an interval I if f of 2 is greater than f of 1 for all x1 and x2 in I, with x2 being greater than x1. The function would be decreasing on that same interval if f of x2 is less than f of x1 for all x1, x2 in I, and x2 is greater than x1. And here's some graphs to show what this would look like. The question is, how do we determine what that interval I is? The following theorem is going to help us figure out those intervals. This theorem is based on the mean value theorem. We're going to assume that f is continuous on an interval I and differentiable on all interior points in I, that is, not at the endpoints. If the first derivative of the function f is positive, that is greater than 0, at all interior points on the interval, the function is increasing on that interval. If the function derivative is negative, that is less than 0 on all interior points in I, then the function is decreasing on that interval I. That's going to give us a way of sketching graphs of functions without a graphing calculator. Let's see if we can use this to sketch the following function. We know that it's continuous on negative infinity to infinity, and it's going to satisfy the following conditions. The first derivative will be positive from negative infinity to 0, from 4 to 6, and from 6 to infinity. The first derivative will be negative on the interval 0 to 4. f prime 0 is undefined, and f prime at 4 and at 6 are the same number, they're equal to 0. Let's sketch this on a number line. Because I know that f prime is positive on these three regions, I know the function is increasing. I know the function is decreasing from 0 to 4. I also know that something's going on at 0, at 4, and at 6. So let's first tackle what happens when f prime of 0 is undefined. It could mean that there's an infinite slope there, but we have to remember that this function is in fact continuous. So I could have some sort of peak there. So it could look something like this or like this at that x value. But if I go from increasing to decreasing, I know it can't be that situation. At 4 and at 6, I know I have the slopes equaling 0. So let's see if I can see how this could look. I've gone ahead and sketched what it could look like if I was increasing and then decreasing, where at 0 I had an undefined slope. If at 4 I have a slope of 0, I think that's the moment where I switch from a negative slope to a positive slope, that is a decreasing function to an increasing function. I have another point where the slope is 0, but it always stays with a positive slope, so I think I'm going to have what I call an inflection point at 6. Now notice I don't have a very beautiful graph, and you don't have to on exams. But I just need to be able to tell that you understand where these slopes are negative, where the slopes are positive, and where they level out to 0. Let's do another example. Let's find the intervals of increase and decrease for the following function. f of x equals x times e to the negative x. The first thing I need to do is find f prime of x. Using first the product rule and then the chain rule, this is what I get my first derivative to equal. I can't do anything with it in the form I have it, so I'm going to factor out that e to the negative x in order to be able to set this equal to 0 to find my critical points. I know that e to the negative x can never equal 0, therefore my only critical point is when x equals 1. Therefore I know that to the left of 1 and to the right of 1, each of those intervals will have the same type of slope, either the same positive or the same negative. Alright, so let's figure out what the slope is to the left of 1. I'm going to use my favorite number, 0, and I find that the slope at 0 is positive, therefore everything to the left of 1 has a positive slope, which means this is increasing. Now let's pick any number to the right of 1. I'm going to use something crazy like 101, just to show it doesn't matter what I use. Alright, e to the negative 101, I know that's a positive number, and 1 minus 101, that's a negative number. Therefore, on the right of the critical point 1, I have a negative slope, therefore I have a decreasing function. So you can see in red my function and in blue my derivative. We do in fact see that the derivative is positive all the way up to the point 1, and the derivative is negative to the right of 1. And you can see that in fact the original function f of x, it is an increasing function to the left of 1 and a decreasing function to the right. Let's do another example. Let's look at the example f of x equals 2x to the third plus 3x squared plus 1. To find when the function is increasing and decreasing, we need to find the critical points again. And again, we're finding them by setting the first derivative of x equal to 0 to find out when it's 0 or when it's undefined. The first derivative of this function is 6x squared plus 6x. Again, to set this equal to 0, I'm going to have to factor in order to solve this. I could even pull out another 6, and I find I have two critical points, when x is equal to 0 and when x is equal to -1. Notice I can divide both sides by that 6, the constant, and that doesn't play into this at all. So I'm going to have three separate intervals. I'm going to have from -infinity to -1, from -1 to 0, and 0 to infinity. So I'm going to see what happens first from -infinity to 1. I'm going to pick a test point of, let's say x is equal to -10. So f prime of -10, that's -10 times -10 plus 1. That's -10 times -9. A negative times a negative is a positive. So that means I'm going to be increasing in the section from -infinity to -1. Let's go ahead and pick a point between -1 and 0. Let's pick -0.5. In this case, I have -0.5 times -0.5 plus 1. I have a negative times a positive, which will be negative. So my function will be decreasing from -1 to 0. Finally, let's do a test point above 0. Again, I'm going to pick a crazy number because it doesn't matter as long as it's within the interval 0 to positive infinity. So I'm not going to pick 0 because that is on the border, but anything above 0 is fine. And I don't even care what this works out to be, I just know my result will be positive. So I know my function increases from -infinity to -1 and from 0 to infinity. And I know the function is decreasing from -1 to 0. And if I graph this on Desmos, I would find confirmation of this. And I found out by graphing my derivative in the original function that in fact the function is decreasing from -1 to 0, and I can see my derivative is below the x-axis. That means my y value is negative. That means my derivative is negative. So my graph matches what I found through calculus. So the next step, once I've found my intervals of increasing and decreasing, is to find out if I have a local max or min, or a point of inflection where there wouldn't be an extreme point. This is going to lead to our first derivative test. Through all this, we're going to assume that f is continuous on an interval that contains a critical point c, and that the function is differentiable on that interval containing c, except possibly at c itself. If the derivative of f changes sign from positive to negative as x increases through c, then c is a local maximum. If, however, f prime starts negative and then goes positive as x increases through c, then c is a local minimum. If f prime stays positive or it stays negative as you go through c, there is no extreme value at c. And I've drawn graphs of these three situations. Let's do an example. Let's find areas of increasing and decreasing and the local extrema for the function f of x equals 3x to the fourth minus 4x cubed minus 6x squared plus 12x plus 1. First, let's find the derivative so we can find the critical points. Once we find the derivative, we set it equal to 0, and then we factor. On an exam, I'm not going to expect you to be able to factor x to the third like this, but if you're doing homework and you run across one of these problems, you can always use a tool like Wolfram Alpha, which will help you factor something in this form. But when I factor it, I get the following. I get that x plus 1 times x minus 1 all squared times 12 equals 0. Again, the 12 isn't going to matter, but I get two critical points. I get x is equal to -11 and x is equal to 1. So I know I've got three areas to worry about. I'm going to do three test points, -10, 0, and 93. For my first test point of -10, I have a positive 12 times a -9, and it doesn't matter what goes on in the parentheses here because when I square it, I'm always going to end up with a positive number. Therefore, I know I've got a decreasing function from negative infinity to negative 1. From negative 1 to 1, when I plug this 0 in, again I get a positive times a positive, and negative 1 squared is also positive, so I'm increasing in that section. For 93, it looks like everything is positive, and again that means I have a increasing function. If I use my first derivative test, if I know I'm going from a negative to a positive slope, then I know that I have a local minimum. If I go from a positive to a positive, it means that I have no extrema at the point. So at negative 1, I have a local min, and at 1, I don't have an extrema. And if I graph this function and its derivative, I see that that in fact is what happens. If I have one local extrema on a certain interval, then I can say that it's actually an absolute extrema. That is, if f of x is continuous on an interval I with exactly one extrema at point C, if it's a local max at C, then f of c is an absolute max. If a local min occurs at C, then f of c is an absolute min of f on that interval I. Now let's talk about concavity and inflection points. If I have a graph of a sine function, this is from negative pi to pi, when I have a graph that's concave up, that means over the interval, the first derivative is increasing. That is, the rate of change of the first derivative, which would be the second derivative, is positive. If I have a concave down, that is where my slope is constantly decreasing. That means the rate of change of my first derivative, which is my second derivative, is negative. And these are our tests for concavity. I can also say if the sign, sign, of f double prime, the second derivative of f, changes sign, then I have an inflection point at that point C. At that point, f double prime in this graph is equal to 0. However, just being equal to 0 does not mean there's an inflection point. For instance, at these 2 points, at the min and the max of the concave down and the concave up sections, at that point the second derivative is also equal to 0. However, in the first case, I have a positive rate of change of the first derivative of f, and if I draw the little tangent lines, you can see that the rate of change of the slopes of those tangent lines is continually increasing, getting bigger and bigger. So even at that point where the second derivative is equal to 0, since f prime is still increasing and it's still positive, that means that is not an inflection point. It's not until I get to this point where the rate of change of the tangent lines start decreasing, and that's when I have a point of inflection. Here is another example of where the second derivative in this case is not defined, and that is also not an inflection point. This leads us to the second derivative test for local extrema. If I have a second derivative continuous on an open interval I containing a point C such that f prime of c is equal to 0, if the second derivative at that point is positive, then I have a local minimum at C. If the second derivative at that point C is negative, then I have a local max at C. If the second derivative at C is equal to 0, then the test is inconclusive. To demonstrate this, I can go back to the example we talked about earlier and find the second derivative of that function. I took my 2 extrema values, my -1 and my 1, that is my possible extrema values. At x equals -1, if we plug that into the second derivative, we find that it is a positive number, which indicates it's a minimum, just like we found before. At x equals 1, the second derivative test is inconclusive because the first derivative is equal to 0 at that point.